All right, so as promised, we're going to look at a little bit more complex momentum problem. So pen's giving me a little trouble here. I think I need to go with a different color. Let's go with blue. So this is going to be momentum, and we're looking at momentum in the case of angles. And so let's talk about the idea of pool balls. So if here's my cue ball, and let's call cue ball A. So let's say that I hit A, right? And actually, let's do this like this. Let's say that it's going to hit B, right? And let's say that that my pocket, my pocket is up here, right? So what I want is I want B to go from its, I want it to go at an angle like this. And so let's say this is my initial vector right here. Let's say that angle, if I continue that out, that angle that I want right there is a 60-degree angle off of that. So, but let's say that when I impact that, of course, I'm not going to be able to hit it dead on. I'm going to have to hit it at the bottom of the ball right there to get it to go into the pocket at 60 degrees. And so that's going to send my A ball off in another direction. And let's just go ahead and define that angle that the A ball goes off at 30 degrees. All right, so let's redraw my A ball here. So this is my A final position, and so then my B final position is going to be in the pocket. Yay! All right, so so here's the question: if I start with these pool balls, and let's say that they all weigh the same. Let's say that they all weigh 0.17 kilograms, and let's say that my initial pool ball, I can smack it at about 4 meters per second. So with that information right there, I should be able to figure out then the velocities of both of these. We already know the angle. This is 30 degrees down here to the right, and this one we could say is 60 degrees to the left of the initial vector. So important to make sure to mention that. All right, so so let's go ahead and calculate this real quick. Well, if you look at this, we've got 3 vectors here, and we can take this and find out our initial momentum, because it's just going to be my 0.17 times 4.0, and that's going to be, let's see, that's going to be 0.68. So my initial momentum right here is 0.68, which means that if I had transferred all of that momentum to this ball, because it has equal mass, it would have gone, and this vector right here is still 0.68, right? Because if I would have hit that dead on, it just would have transferred all that momentum. The cue ball would have stopped still, and then the B ball would have gone with a momentum of 0.68, 4 meters per second, same mass, straight out this way. So here's my triangle right here. I got all my vectors. So I'm just going to go ahead and redraw this triangle. Let's go ahead and get a fun color here. So I've got, actually, let's go ahead and use the colors that I have here. So here's my original trajectory, all right? And let's go ahead and I need, let's see, my B ball was, so it's going to come off at 60 degrees. Actually, let's go ahead and start with the way that I drew it on here. I just drew this vector right here. There's my 30-degree vector. Now my other vector was 60 degrees off of here, which would have meant it also to then be, if I could just draw this just to kind of show you, it would be 60 degrees here. So I'm just going to continue that so that I keep these vectors all the same. So there's my B ball vector. So then these two right here, you can see are going to form a right angle, because I've got a 30 degree and a 60 degree. So this coming off of here, 30. So there's my 90 degrees right there, which is what I have right here. I know it doesn't quite look exactly perfect, but this is pretty simple now, because I know that this right here, let's keep these, is 0.68, right? I know that this angle right here is 30 degrees, so I can figure out these other vectors quite simply, actually. So let's go for the B ball right here. So the B ball, the momentum final of the B ball, right, is going to equal, let's see, this is going to be the sine of 30 equals, this is the hypotenuse here, so I have the opposite. So let's go the B ball's final divided by 0.68. So what's that going to give us? Let's see, I got that here somewhere. I'm just trying to look at what my answers are. It's going to give me 0.34 as my momentum final here. Well, I know that that momentum final equals mass times velocity final. And so the velocity final is what I want to know. So I know that my mass is 0.17 kilograms, right? So all I'm going to have to do is take my 0.34 here and divide by my 0.17, and that's going to give me my velocity final, which in this case equals 2 meters per second. And I know that that is 60 degrees. Oops, 60 degrees. I'll go ahead and rewrite that. So I got 60 degrees, and let's say to the left. All right, now what about the A ball? Well, it's this part of the triangle right here, so this is going to be the cosine, right, of 30 degrees, because this is the CA function. So kind of skipped over that because we've done that a lot, but we're looking at the cosine of 30 equals the adjacent over hypotenuse. So that's going to give me my P final for my A ball, and over 0.68. So what does that equal? Looks like that's 0.59. So my momentum final of my A ball is 0.59, and I know that that equals 0.17 times some final velocity, right? Because momentum equals mass times velocity. So divide 0.59 by 0.17, and I'm going to get 3.47 meters per second. And that's going to be going at 30 degrees to the right, okay, of the initial vector. So not all that difficult, because one of the things about pool balls that's nice is that they're all the same mass. So that simplified this quite a bit. If you had different masses in here, it get a little bit more complicated, but not too bad, and you could still do it as long as you knew what those masses were. All right, so here you go. This kind of shows a little bit more of a complex idea, and sorry about the fastness and quickness. I had to get this done as quick as I could. I'm running out of time, but hopefully this helps with some of your momentum problems.